Alright, hello. I just wanted to cover some quick things with using OpenRocket. So first off, this is the UI that you will get to use. Obviously, nothing's entered in here yet. But for now, what we can do is I can just quickly show you some basic installation stuff. So, first off, you have kind of the OpenRocket website. It's an open source system. It's pretty good. It obviously brings up thrust curve, which is this is a great database. But anyway, one of the things you can do in OpenRocket is you can import motors from here, but I'm not going to discuss that right now. So tons of information here. They have a wiki in here. Wiki is quite helpful. Probably the most important section of the wiki is right in here. They have all the download stuff, or Linux if you're very epic. There's also this thread on the Rocketry forum where they basically link to very similar stuff, but if these aren't working for you, then this should probably work for you. There's just weird things that, happen. Besides that, just assuming you get all this installed properly, let's look at the actual OpenRocket interface. So this is what it will look like when you have nothing. I'll just open up. So for example, this is what a completed rocket might look like. This was our TARC rocket, and this has everything made perfectly. So every single one of our components on board the rocket was shown by one of these components or one of these body tube sections. And this is one way of doing things, but for our purposes, it's unnecessary. So what we're going to do is we're just going to start from scratch, and we're just going to start doing things. So first step we want to make is put on a Nosecone. For now, we're going to use basically arbitrary numbers for what to do. Obviously, I run in metric normally. Honestly, I don't even remember what the numbers are. I'm just going to see what's reasonable. About 5 centimeter body tube. It's alright. I'm just going to make this a conic nose cone. So, as you can see, OpenRocket has already started showing us a couple of things here that are pretty important. The next thing is, as you will notice, just from the UI here, I just put down our first component, but now let's actually look at what's going on. You can see here in this design part, and again, sorry, this is kind of unorganized. I'm just putting this together real quick. I might make a better version of these at some point, but rocket design, this basically lets you actually do the design work and place in components. You have motors and configuration. This lets you pick, there's a thing called motor mount tubes, where in each motor mount tube you can put in a specific motor, and you can choose the motor and save configurations in this window. And then here, you can actually do the full simulation of your entire flight, and you can get all the information that you need. So, let's go back here. To go into a little more detail here, basically some of these, everything here, aerodynamics are simulated on. Everything in here and in here, aerodynamics are not simulated on. Now, technically here and here they are, but that's only after they're deployed, because Obviously, a parachute is not generating any drag when it's stored inside the rocket, hopefully at least. So these are going to kind of be the main sections. These are probably the two. These are, I'd say, this, and this are the most important. Here is kind of a tree that shows everything that's going on. This is your top level. This contains everything. This contains you have one of these for each stage of your rocket, which are the sections that will separate, and then you'll have one of these for each component. So, besides a nose cone, we can add on a body tube. For us, we have a very short body tube, so I'm just going to model that real quick. I'm kind of loosely following our design, but it's not too closely, to be honest. It's very short. It's probably about 1 centimeter. So next, what we're going to do is create a new stage. So we currently have it calls it a sustainer. It's fine. We could probably rename this if we wanted to, but yeah, I will. I'm going to rename this to the capsule section. So next, we're going to create a new stage I'm just going to call it the booster section. Close. Alright, so in this booster, basically what this does in each stage is these are points that along the rocket where it will have a clean break. So the booster section will first get a semi-short body tube. I'm going to make this parachute, I'm going to make this nose cone shorter. There we go. Okay, so back into this section. Then there's a transition. This, honestly, is everything on here is basically self-explanatory. Let's just make him 6.5. I don't know. And then we're going to add on another big body tube. Our rocket looks something like this, I think. I don't really know. And if you notice, because we've selected basically most of these things won't go on unless it's on a body tube. And now that we're on a body tube, we can attach everything that we need. We are going to strategically not worry about what basically any of this stuff actually means. And OpenRocket allows you to simulate things pretty accurately and to kind of place in all the components. However, we're not going to worry about that. All that we're concerned about is, and now we can see right here, it's showing us, as you can see over here, center of pressure is this red dot, center of mass is this blue and white dot. And for a stable rocket, you want your center of pressure to this is your center of pressure. You want your center of pressure to be behind your center of mass. Obviously, this is unstable right now, so we will add these fins. Freeform fins are okay. Electrical fins work. Trapezoidal fins work. The problem with freeform fins is they're just kind of wonky, and it doesn't simulate them as well as it should. Trapezoidal fins are kind of where it's at. These work very well. Honestly, I guess we'll just increase. No, I won't. I'm going to increase this. I'm pretty sure how this looked was something like this. No. What's this? Yeah, it was something like that. And it was swept back a little further. Yeah. And honestly, it's probably just a little, just comically oversized fins, basically. But, it's that way for a reason, because it makes everything stable. Next, we can, and as you can see, we made these on this body tube, so it's kind of like a component attached to a component. There are only 3 more components that we're probably going to add. I guess 4, but one of these will be the engine block. typically SD's rockets use an engine block. Kind of bigger rockets will use an inner tube, but really either work. The only difference is just how much mass they're given. So we will use an engine block. This will not be perfectly accurate. We're going to make it about this big. Yeah, that's obviously not the exact size, but it's fine. What we can do is, now that we have a body tube, oh, is this engine block? Sometimes I forget how to add parts in. See, what I can do is I can select this guy as a motor mount, but this is one of the only annoying areas in OpenRocket. I'm just going to add an inner tube because I know for a fact that it works well. Here we can see motor mount. Let's just check this. Close that. This is not exactly what how SD's rockets work, but it's fine. This inner tube. Now it's very happy. We can just make a new configuration. Basically, for each of these configurations, it's a different option. So for this, we can double-click this. Double-click you. Hang on. So we'll select him, and then we'll pick a motor right here. Sorry, I'm slightly rusty on this, but we'll pick a motor, and yeah. As I was saying, OpenRocket's pretty detailed. They have a lot of motors, including some big boys. These aren't even in production anymore. Fascinating. But yeah, they got your quarter A's all the way up to your 8000s. So yeah, they got quite the range. This is a special motor. 25,000. Oh dear. Anyway, so let's not select that motor. It would dwarf the rest of the rocket. But one of the things that's nice is you can just trim down the number of motors that you have. So we're looking for a C65 from SD's. Now we can also clear all, and we can only select SD's. Here we go. We have a C6. Obviously, that's your thrust. And this actually does not list the dash something. You select that directly in here. This is important for more advanced rockets where you can change the delay time yourself. Ooh, fancy. But for now, it's not going to worry about. We'll just pick the C65 because that's what we use. And we hit OK. And look, we have a nice little motor sitting in here. So, our stability is not great. It's 0.175 caliper. There are better ways to calculate stability. And I will choose to not explain those ways because, well, I guess I will. You basically calculate the percentage of the body tube that these are apart by. So they actually list exactly how far away they are. So we can see this is 25.9 minus 24.8. So they're 1.1 centimeters apart. It also very conveniently lists the entire length of your rocket, which is 37.3 centimeters. Times that by 100 to get percentage. And you can see that they are about 3% of the body length apart from each other. Now, this is not really good enough. The general rule is that you want between 8 and 18% to be the rough distance between them. Any less than 8%, you get to be understable, and it won't correct properly. Any more than 18%, you invoke a dark magic called overstability. And, yes, you can apparently make your rocket too stable. How? I don't really know. Anyway, besides that, we've basically added in every single component that we can need. The one last thing that we can do is we can use something called a mass component. Oh, sorry. There's one other thing that we can do that's only of marginal importance. We can just add in this little thing called a parachute. You can also, I believe, you can't directly add in recovery wadding, but you can just add in a mass component here and just give it the massive recovery wadding. So 30 centimeters, that's reasonable-ish. Honestly, this is just a rough simulation, doesn't really matter. And we're not even supposed to simulate the down flight anyway, so this parachute's kind of not necessary, to be honest. So we'll just put in this little parachute. It's just good to know. You can adjust how long deployment takes, which is a pretty nice feature. Shroud lines, these are important for things that we won't deal with right now. And you can change the coefficient of drag of your parachute and the diameter of your parachute. One of the things that you may have noticed is that nowhere here did we really enter in the coefficient of drag. And there's actually nowhere that we can do that. And the reason is because OpenRocket simulates all the aerodynamics for you much more accurately than just assigning some coefficient of drag will. So the parachute's the one place, because OpenRocket can't simulate parachutes. You just find this experimentally. But there are roughly accepted values that you can just look up. So that's the main thing for the parachute. Now for the real last thing, inside the nose cone, we can just add a little bit of mass. Now, in reality, we don't have a chunk of mass inside the nose cone. However, you may notice that I never adjusted the masses on any of these parts. And the reason for that is that it doesn't matter. This simulation is not a complete simulation. A complete simulation would have every single component placed in the exact right position. But that's way too much work, and we aren't going to do that. What works just as well is if all you try to pay attention to is where's the center of mass and what is the total weight. That's really all that matters. So what you can do is just in basically an arbitrary position, place down a mass component, just give it some mass. Let's say 10 grams. No, let's say a little more. Let's say this. Let's say, I don't even know what I said, honestly. It just doesn't really matter. What you can do is you can increase the mass until you get to about the right amount of weight. And then you can just move this. Sorry, let's not move it that way. Oops. You can just move it around, and as you can see, I'm just moving this around, and the center of gravity is changing. Now, once again, obviously, there is no 12-gram mass sitting here, but the point is that because we're simulating the correct mass, which is once again an arbitrary mass, if you want to pick an actual mass, you can go through and fix this, and actually mess with mass numbers and get this mass correct, get this position correct. But that's not the point right now. That's easy for anyone to do. You just change masses and positions. As for center of pressure, OpenRocket is going to be far more accurate than you could ever hope to be manually. So you just let it calculate it. There's nothing else to that. And just make sure, generally these, your tube, everything is accurately on there. If you want to, you can add on a little launch lug. I mean, you can, right here or so. This launch lug is a little too big. Let's put you in millimeters. Something like that. That's more like it. Another interesting thing, you can actually rotate your rocket around to see how it looks. Now, obviously, the launch lug does not actually belong there, so we can just, move it. So now it doesn't directly line up and be obstructed by a fin. But you can like spin your rocket around. But now we have a complete simulation. Now, obviously this is not exactly precise, however, I don't care. All that matters is it's stable enough. In fact, I'm just going to make this a little more stable because I don't trust it completely as is. If we wanted to, we can just do a quick test of this. So let's do 25.9 minus 22.5. Divide this by body tube length, 37.3 times 100. And this is stable enough. Not comfortably stable, but stable enough. And this could be fixed later. So now we check, okay, we have our motor installed. We have everything installed on the rocket that needs to be installed. So now we can make a simulation. So the way you do this is you hit a new simulation, and oh, that's a lot of options. Wind speed, this is fine. Just pick a wind speed that you think is appropriate. This is correct. You, if you want to, you can adjust temperature and pressure as you please. How is this 3 millibar? That seems suspiciously low. They should be like 1 bar-ish. Okay, yeah, that's more like it. 1013 millibar. So we're just going to not worry about it. It just had weird, like, standard points, but 15 Celsius, 1013 millibar, that's very reasonable. This can be picked later. This just changes things. That shouldn't really matter that much. Okay, important things. Your launch angle is basically if your rod's like this or if your rod's like this. So, yeah. We're going to stick with 0 for now. You can change the angle if you want to, but we can stick with 0. Next, the last major thing is how long your launch rod is. Now, the ones that we have are 4 feet. So, like the small scale pads that we use are 4 feet in length, as far as I'm aware. So, we can say this is the default. And now, hopefully, this will remember everything. So, let's just make sure. This time step is actually slightly higher than what our spreadsheets use. It has a default to a 20th of a second, but OpenRocket is accurate enough to where it doesn't really matter. Yeah, do not worry about this. This is fine. What does it say? Yes, this is sufficiently accurate for almost all purposes. It's correct. It's using an extended Biermann. This is how it calculates aerodynamics. Don't worry about it. This is how it actually simulates things. And we'll just make the time step to be 0.01 to it be in line with the spreadsheet. We'll say this is the default. Make sure everything is good. And we'll simulate this. And it should be pretty fast. So, ready? Boop. Done. It's already done. And let's plot everything. So, this is a little crazy, but it's okay. This provides actually a little bit more information than the plots that we made on Excel. So first thing to notice here is our acceleration. I think it's being a little silly here. I don't know how it starts as -10, but it's for such a short period of time that no one cares. And our vertical velocity essentially starts at 0, so it just doesn't matter. So, oh dear, what have I done? The important things here, you look at your acceleration. Hey, this looks familiar. It's almost like it's the thrust curve of our motors. Shocking. Next, you'll see velocity, and it follows that same kind of accelerating, and then it has a little acceleration, but it keeps going solidly, and then it stops accelerating, and then it's gradually decreasing. It slows down the decrease rate because of drag slowing down, which you can also see in the negative acceleration lowering. Right here, it hits apogee, which is shown. Let's zoom in here. Apogee is where it goes up and then falls back down. Evan refers to this as zenith. I don't know why. But the other important thing is vertical velocity changes from positive to negative. Now, OpenRocket has not precisely timed where this happens. It's off by 4/100ths of a second. How dare it? But let's zoom out again. Basically, everything on here is very reasonable. So this is being irritating again. There we go. The last thing that OpenRocket simulates that we actually don't care about, well, we do care about, but it's not on the spreadsheet, is parachute deployment. As you can see, you have a pretty big spike. This is why we have shock cord, because, and sorry we don't use a string, because there's a lot of force right here. It would just tear string apart. And you can see it's the vertical velocity. It's in free fall, and then suddenly, oh, acceleration 0. Velocity is constant, and it's just slowly falling to the ground. So that is OpenRocket. The other important things to note from OpenRocket is, besides the plots, it actually gives you a lot of great information right here. It gives you, do not worry about an optimum delay for now, but let's do this left to right. It tells you that, obviously the number simulation you did. You can also, I believe you can name the simulations. So, yeah, you can. It tells you which configuration is flown in. It tells you velocity off the rod. This is important, but we're going to not worry about it. Basically, aerodynamic stability doesn't take into effect until you're already going pretty fast. So you need to get going pretty fast off the rod if you want to be stable sort of flight. So you want this number to be high enough. This is high enough. It's fine. These rockets are designed to work, so you shouldn't need to worry about this. Well, if we trust SDs at least. Apogee, important number. Pretty straightforward though. We have velocity of deployment. You should generally watch for this. If your delay charge is really high, you're going to deploy a parachute when you're going really fast towards the ground. And if you deploy it at a really high speed, it's possible to rip your parachute because there's so much force on it when it's deploying. But this is an okay speed. This, again, don't worry about. Max velocity, straightforward. Acceleration, straightforward. It's about 10 Gs. It's all right. Time to gap, apogee, pretty straightforward. Total flight time, pretty straightforward. Just when it lifts off to when it obviously hits the ground. Ground head velocity, pretty straightforward. You generally want to keep it below, like 8 meters per second. Depends on how big the rocket is, but smaller rockets can get away with hitting the ground faster. So this is obviously a very safe ground head velocity. And we didn't even mess with the parachute. So, yeah. I would just save this. We'll probably save this as, what we'll call it, AP Physics Rocket. Okay. So, that is the main thing. If you have any questions, you can just let me know. But yeah, hopefully this will work. Hopefully installation works for you. So, anyway, see you guys.